Yesterday we started with Gaussian quadrature rule, and I indicated the fact that the motivation behind the Gaussian quadrature rule or formula is that compared to the previous quadrature rules, like what we call the Newton codes quadrature rules. For the Newton quadrature rule, if I have n points, that is n nodal points, the degree of precision of the method will be at most n. At most n. If I take the case of, for instance, the simplest method, the simplest Newton code method, which is the trapezoidal rule, we know that the trapezoidal rule uses 2 points, 2 nodal points, but the degree of precision is 1. So you see that we use 2 points for a lesser degree. Okay, now if you progress to the Simpson third rule, where the degree of precision is 3, and you also use 3 points, yeah, approximately 3. You see that the degree of precision and the number of nodal points is approximately the same. In fact, in this case, it's the same, right? If you go further to the Bool's rule, you will see that we use 5 points. 1, 2, 3, 4, 5, yeah, approximately 5 points. This is 5 to 6 points. And the degree of precision is 5. So you see that the number of points gives you the maximum degree of precision. Maximum. Now, with the Gaussian quadrature rules or quadrature formula, with a lesser number of nodal points, we have a higher degree of precision. If I have n plus 1 nodal points, n plus 1 nodal points, we will have a degree of precision of 2n plus 1. So you see that the number of, the degree of precision is almost the double of nodal point, almost. The difference is just 1. Because the double of n plus 1 will be 2n plus 2, but we have 2n plus 1. So it's almost double. So that is the advantage of using the Gaussian rule or the Gaussian quadrature rule. That is the motivation. N point or n plus 1 point, and then the degree of precision is 2n plus 1. So the degree of precision is almost the double of the number of nodal points. So it means that it gives us a more accurate result. So it means that when you use the Gaussian rule, your integral gives you a good approximation with a few function evaluation. Is that okay? Is that clear? So that was our introduction. And the description of the method is given by a theorem, which we call the Gaussian theorem. According to the Gaussian theorem, if I have n plus 1 nodal point, that's something you should be able to explain to yourself, right? Without having the text or something. For each of these methods, you should ask yourself, what is the purpose of this? What is the degree of precision? How do I proceed to get the rule? So those are the small, those basic questions you should be asking yourself. Now, according to the theorem, if I have, let's say for instance, I want to derive a Gaussian rule. First of all, I need a polynomial of a certain degree. Let's say a polynomial of degree n plus 1. Because for n plus 1 nodal point, I need a polynomial of degree n plus 1. So I take a polynomial of degree n plus 1. A polynomial of degree n plus 1, actually there are n plus 2 coefficients, right? Because you start from 0 up to the degree. So it's a degree plus 1. So if you have a polynomial of degree n plus 1, there are a total of n plus 2 coefficients. But here, the condition that we impose on the polynomial is that the integral from -1 to 1 of x to the k times the polynomial dx is imposed to be 0 for k running from 0 to n, meaning that we have a total of n plus 1 condition imposed on the polynomial. Instead of n plus 2, we have n plus 1 condition imposed on that. So it means that the system that we obtain is overdetermined. You have more unknowns than the number of equations. So in that case, you have many solutions, right? When you have an overdetermined system in general, you have more solutions. So that is why yesterday when we solved, we obtained a relationship between an and it was a1. It was a1 and a3. Yeah, I think so. Yeah, a1 and a3. So you see, you have, because for each a3, you have a corresponding a1. So it means that there are many solutions. So the solution is not unique because of that. So you solve that system, you fix one value of the parameter, you get the other one. But the advantage here is that the polynomial that you obtain will be a multiple, of course, a scalar multiple of any other polynomial. In other words, if I get a polynomial, let's say q, and a different person gets another polynomial q, the polynomial are almost equal, because the only difference between his polynomial and my polynomial is just a multiple. If I multiply his polynomial by a certain value, you will obtain mine, right? If I multiply his polynomial with a certain constant, I will obtain my polynomial. So I can say that it's unique by a constant multiple, that's all. But the roots are the same. Because remember that if I have f of x, I find the root of f of x. If I multiply f of x by alpha, where alpha is a real number, it doesn't change the root. The root is still the same. So regardless of the way you proceed to obtain your polynomial, and regardless to the way I proceed to obtain my polynomial, our x case, the root or the nodal point for the rule are exactly the same. We have the same nodal point. All right, because remember that for a quadrature formula, it is a sum of the way the function at the nodal point. You evaluate the function at the nodal point. So that's the formula. So if the nodal points are the same, and we also compute the weight, they are the same, we have exactly the same formula. So at the end of the day, we all obtain the same formula or the same rule, the same quadrature rule, or the same quadrature formula is the same. It's the same. I hope it is clear for everybody. Okay, so that is it, and that's what we did yesterday. We applied the methodology to the 3-point quadrature formula. Because we took 3 points, we say, okay, polynomial of degree, okay, if you want 3 point, it means that our q is of degree 3. Because remember, the number of nodal points correspond to the number of, to the degree of the polynomial q. 3 points means our q is of degree 3. So pose the condition of the theorem, compute the coefficients, solve for the roots, and you integrate the cardinal function to get the weight, Or you use the method of undetermined coefficient, the way we proceeded yesterday, right? Because yesterday, the way we proceeded, we used the method of undetermined coefficient, meaning for n point quadrature of Gaussian quadrature rule, if you have n point, it means that we also have n weights, right? But we know that if you have n point, if you have 3 points, the degree of precision of the rule will be what? 2n plus 1. If you have n plus 1 point, it will be 2n plus 1. So we use this information for the 3-point rule, or 3-point Gaussian rule. We need a polynomial of degree 3, right? Because 3, the degree corresponds to the number of nodes or nodal points. We need a polynomial of degree 3. And for a polynomial of degree 3, the degree of precision is 5. Because if I want to write 3 as n plus 1, it will be 2 plus 1. So the degree of precision will be 2 times 2 plus 1, which is 5. So the degree of precision is 5. But in the notes, because we want to find the coefficient of a third degree polynomial, in fact, we did it already. Now we are looking for the W's. There are three W's that we need to determine: W0, W1, W2. Now, if we want to use a degree of precision in order to apply the degree of precision to apply it to our method of undetermined coefficient, in order to determine W0, W1, W2, remember that we will need to indicate that the method is exact for polynomial degree less than or equal to 5, but we don't need to go up to 5. Because if we say for polynomial degree up to 5, it means that we impose 5 conditions, but we don't need to go up to 5 conditions. We only need 3 conditions. So to impose 3 conditions, we take k equal to 0 for the first, k equal to 1 for the second, k equal to 3 for the second, for the third. So meaning that the polynomial that we will need here, it will be of degree up to 2. So that's what we use in the note. It doesn't mean that the degree of precision of the method is 2. No. It's 5, but we don't need to go up to 5. We only need to find 3 unknowns. So for 3 unknowns, we need to take k equal to 0, 1, 2. It gives us the 3 conditions for the 3 unknowns. So that's why in the note, it is mentioned that the method is exact for polynomial degree less than or equal to 2. Yes, it's true because it's up to 5. So if I say even less than or equal to 3, it's still true. But the degree of precision actually is 5. Okay, I hope that with this, there will be no confusion. I took time to insist on this so that next time you will not say you don't understand why here we say that it is exact for this, whereas the degree of precision is 5. And explaining because we only have 3 W's, 3 weights to determine: W0, W1, W2. So there are 3 in total. And if we want to write that the method is exact, in order to determine this, we will need 3 conditions starting from k equal to 0. So we'll stop to polynomial degree less than or equal to 2. I hope it is clear for everyone. Okay, so now let's continue with the method. So we solve, let me go back even to that, the method of, okay, so this is where we stopped yesterday. but it was a bit fast. This last part we went. I mean, the speed was not low because of the time constraint yesterday. So if I come back to this is what I was talking about. This approximation, we said that this approximation, we can make it equality. Whenever f is a polynomial degree less than or equal to 2, we use 2 here instead of 5 because we need to determine 1, 2, 3. You see that we have W0, W1, W3. So to determine these 3 coefficients I need, so here we have three unknowns. 3 unknowns. W0, W1, W2. So there are 3 unknowns in total. So how many equations do I need to determine 3 unknowns? I need 3 equations. So we need 3 equations. 3 equations. So if I need 3 equations, it is enough for me to use f of x equal to xk with 3 values of k. So I can take k to be 0, 1, 2. So with this one, it will be enough for me to get all the 3 weights. So the rule itself, the degree of precision of this rule is 5. Is 5. Why? Because this 5 is 2n plus 1. Right. It's 5, this one. And this should be 2n plus 1. But if you take n plus 1 equal to 3, so let me explain here. We have n plus 1 equal to 3 nodal points. So the degree of precision is 2n plus 1, which is 5. So this 5 here, actually, this one, for the 3-point rule, the degree of precision is 5. But the fact that we are using polynomial degree less than or equal to 2 is because we need up to that to determine 3 unknowns. We don't need to use up to 5. We don't need, it's useless to go up to 5 because 3 equations are enough for me to get a unique weight. Please tell me if you understand that so that I will not insist again, I will proceed. I want you to understand that so that this will not confuse you. What is written here? Here, it is not mentioned that the degree of precision is 2. No. It will be exact for polynomial degree less than or equal to 5, but we need to stop at 2. Is that clear for everybody? Okay, now if we take these 3 functions, f of x is equal to x to the k, where k runs from 0 to 2, those three values, we write that this rule is exact. So that's what we have been doing here. We wrote that this rule is exact, means that it's not an approximation, it means that it's equal. So that's why you see equal here. This is an equal. It's no longer an approximation because here we wrote an approximation. This is exact, that's why it's equal, and here also it's equal. So for each of these value of f of x, we substitute that into this equation, we obtain a system. So if you rearrange this system, we get this one, and if we solve this, we get that. Okay, now let's see how to solve it. Maybe that's what you need to see. Okay, so in order to solve it, I think it will be better for me to copy this, move to the new slide, and do that, because I don't want to overload as I did here, and it becomes very dirty, messy. Everything I wrote here was just for explanation purposes. Okay, so let me okay, so what I will do. Oh. Okay, so what I will try to do is to copy this. Okay, so I think I will write the rule first, and I will go step by step and do everything, because I doubt that it is clear for everybody. So I will try to do that. Okay, so let me share the new slide with you. Welcome, Simeon. You are too late, Simeon. Okay, so this is the rule, right? And we want to solve for this, right? We have three unknowns. I already indicated that we have three unknowns, and we need three equations, right? Okay, but we know that since the number of nodes here, node at point, you can see we have 1, 2, 3. So we have this x0, x1, x2. So this is a 1, 2, 3-point rule, right? 3-point rule. 3-point rule. Gaussian rule, of course. When we say rule, it's Gaussian rule. So we have n plus 1 nodal point. So which means that n here is 2, right? If I solve for n is 2. Now, the degree of precision of this rule is 2n plus 1. So this is 5. So the degree of precision is 5. Meaning that this rule is actually exact for polynomial degree less than or equal to 5. Right. So let me call this star. So this implies that star is exact because this is an approximation. So the approximation becomes an equality, meaning that we put equal, error term becomes 0. So a star is exact, becomes approximation becomes equal. So we can replace in star we can replace the approximation with the equal sign for any polynomial of degree less than or equal to 5, because 5 is the degree of precision. But for the purpose of finding only 3 unknowns, we don't need to use this, because if you write that, our system will be overdetermined, but we want a unique solution for our system. But for the purpose, right? But for the purpose of finding or determining W0, the weights W1, W2, which are 3 in total, we need instead of this, right? We need 3 equations only. Or we only need 3 equations. We need 3 equations only. 3 equations only. And for that, it is enough to consider polynomials of degree less than or equal less than or equal to 2. That is x0, which is 1, x1, and x2. So that's what we need. We need these three to impose this equality here. So therefore, we can take f of x equal to that polynomial, right? Because when you say equal, it means that we replace f of x with the polynomial. So this will be enough to determine a unique coefficient W0, W1, W3, because you can see we have three equations with this. Now, if I take this and substitute, therefore, there, this becomes an inequality. So this means so if we take k equal to 0, we have the integral from -1 to 1. We replace this, which becomes x to the 0 dx equal W0, this function at 0, because this is 1. So whatever function, if the function is constant equal to 1, this will also be 1, right? So this will be 1 plus W1 times 1 plus W2 times 1. Why? Because f of x, which is x0, is 1, is constant. So it's always 1, regardless of this. Whatever I put there, it takes a value 1. Right? It's constant. It does not change. It does not change. So this implies that f of negative square root of 3 by 5, because it's constant, is the same as f of 0, is the same as f of square root of 3 by 5, which is 1. So they are all 1. So that's why we have this. And this is W0 plus W1 plus W2. So this is the right-hand side. But what about this left-hand side? This is now this side, this part, the integral from -1 to 1, x to the 0 dx is the same as the integral from -1 to 1 of 1 into dx, which is the same as the integral from -1 to 1 of dx, and the antiderivative of this is x. So it is x from -1 to 1, so which is 2. Right. So therefore, for this first case, we obtain the system. We obtain this system 2 equal to that. So 2 equal to this is the same as this equal to 2, right? So W1 plus W2 plus W0, sorry. W0, W1 W0 plus W1 plus W2 is equal to that integral, which is 2. I just rearrange. So it gives us this equation. Okay, similarly now, if you take x equal to 1, k equal to 1, here k is equal to 0. Now, if you take k equal to 1, now we'll be integrating from -1 to 1, x to the 1 dx. And this is x, and the antiderivative of this is x squared by 2. We integrate from -1 to 1. You see that this function at these 2 points is the same. So when I will take the difference, it is 0. So 0 is this left-hand side, this integral, this part. That's what gives us 0. Now we need to substitute the right-hand side. Now what is the right-hand side? F of x here is x, meaning that the value taken by x is equal to its argument. So whatever x is, that's the value of f of x, right? So this will be W0 times f of 0. So f of x here is x. So meaning that f of 0 is what? 0. X is 0. Whatever is here is what I put there. 0 is 0. Now, if I take f of negative square root of 3 by 5, it's exactly the same thing. Negative square root of 3 by 5. It's exactly the same thing. Because that is the argument. Similarly, f of square root of 3 by 5 is exactly square root of 3 by 5. So now, if I come and substitute here, f0 is multiplied by what? By f of negative square root of 3 by 5. So that is the value. So this is times negative square root of 3 by 5 plus W1, f of 0 is 0, plus W2 times f of square root of 3 by 5, which is square root of 3 by 5. So 0 is equal to that. So this implies that 0 is this, or I can write that this is 0. It's the same thing. So I can write negative square root of 3 by 5, W0, this is 0. So plus square root of 3 by 5 into W2 is equal to 0. Now you can see that this is a common factor. So I can factor by this equal to 0. So this implies, or I can factor by that if you want. Negative square root of 3 by 5 factor of W0 minus W2 is equal to 0. We know that if the product of two real numbers is 0, one of the factor is 0. It means that this is 0 or this is 0. But since this is non-zero, automatically this is 0. So this implies, therefore, that W0 minus W2 is 0. So that gives us our second equation. So the second equation, therefore, is W0 minus W2 equal to 0. So this is our second equation. Now, for the third equation, we take k equal to to 2. And therefore, we'll be integrating equal to, so here, let me see it. So f of x here is x squared. So whatever the argument is, I square it. That's what this means. So now here we have W0 times f of negative square root of, so I will square that. So it will be into, now what is here is negative square root of 3 by 5, I square that, plus W1 times f of 0. So here f of 0 is 0 squared, plus W2 times I square square root of 3 by 5. Because of the expression of my function. Now, if I integrate this, so this is so if I evaluate this function at 1, it is 1 by 3. If I evaluate this at 1, it is negative 1 by 3. Right. But because I take the difference, there will be a negative here. So it becomes 2 times this value. So it becomes 2 that. Right. So this is 2 by 3. Right. I hope there's no error. Right. Okay, that's for the left-hand side. And this is equal to what? This is equal to this side. So now, what is this? This is 3 by 5. So I can say 3 by 5 W0 plus, this is 0. Right? So this is 0. 0 times anything is 0. So it will be 0 here. Now, plus this. So this, when I square, it's 3 by 5. So 3 by 5 again, W2. Right. So this implies, therefore, I can rearrange that 3 by 5, right? I can factor that. W0 plus W2 is equal to what? 2 by 3. So now if I cross, I multiply both sides by 5 by 3, this becomes 10 by 9. So this implies that W0 plus W2 is equal to 10 by 9. And this is our third equation. So you see that we have 3 equations in total. So let me group all these equations. So this is our system. So our system is W0 plus W1 plus W2 is equal to 2. The second one is W0 minus W2 equal to 0. And the last one is W0 plus W2 equal to 10 by 9. So this is our system. Now, you agree with me that the second equation, this is the first equation, this is the second equation, this is the third equation. From this second equation, we just see that W0 and W2 are exactly the same. Right. Now, if I add 2 and 3, if I add 2 and 3, I add this 2, I have 2W0, because this will cancel out. 2W0 is equal to 10 by 9. So this implies that W0 is what? 5 by 9. And which is exactly W2. Now to get W1 from the first equation, W1 is 2 minus the sum of W0 and W2, right? W0 plus W2. But I know that W0 plus W2, this sum, if I add this 2, W0 plus W2 is 10 by 9, right? So that is 2 minus 10 by 9, right? So this is 18, so that would be 8 by 9, right? Because this is 18 minus 10, that is 8 by 9, right? So that is our W1. So W1 is 8 by 9. Now, it is simple. Now, I need to check if it's correct. If I add this 3, will I get 10 by 9? If it's not, if I add this 3, W0, W1, will I get 2? If I don't get 2, it means that there's an error somewhere. Then I will have to check, right? So let me write here. W0 here is 5 by 9, 8 by 9, and W2, 5 by 9. Now, if I add this plus that is 10 by 9, plus 8 is 18 by 9. 18 is the double of 9, so 18 by 9 is 2. So everything is correct. Now, so I have all my weight. Now, if I take this weight and substitute into the formula above, therefore, because the rule is what we are looking for, our rule now, consider the integral f of x dx for our rule is approximated by what? We know already W0, that is W0, 5 by 9, f of negative square root of 3 by 5, plus W1, that is 8 by 9, f of 0, the second root, or the second nodal point, plus W2, which is 5 by 9, into the third nodal point, which is 3 square root of 3 by 5. So this is how we obtain our rule. Right. Okay, so I hope with this detailed example, because I took time to explain this line by line, so that none of you will say you don't understand. I hope with this it is clear enough for everyone. Good. Now let us go back to our notes. So this is the rule. It's called the 3-point because we have 1, 2, 3. So it's 3 points. Okay, but the 3 point that we have computed here, we assume that our interval, we are integrating f from -1 to 1. But that can be generalized to an arbitrary interval AB, and that's what we will do. Okay, so what we have done is the 3 points, so you can do the same for the 2 point. Instead of using 3 point as we did, you can use 2 point, and 2 point will be easier, right? You follow the exact same procedure. With 2 point, now your Q will be a polynomial of degree less than or equal to 2. So instead of having this, it will just be this 3. You write this exactly the same way. Please, I'm asking you to do that. If you do it and you cannot get the result, it means you have to make a lot of effort and you have to make it right. This is what you get for the 2 point. 2 point will get this, meaning that your Q that you get, these are the two roots that you get for that polynomial. And the weight, if you follow the method of undetermined coefficient, the weight W0 and W1 will give you 1, 1. So that's what it means. So please do this homework. So this is a homework. I encourage you to do it. Okay, now if you use the transformation, x equal to this expression, that is 2t minus b plus a by b minus a. If you use this change of variable, you'll be able to convert the integral from -1 to the integral ab. And this is the formula for the change of variable. Sure that the time is against us, otherwise I would have done this for you to see, but I encourage you to do that. Take this as your new x. This is x is in the interval -1, 1. And then, okay, let's look at this. You see that we want it to be in the interval AB, right? And this is the change of variable. You can see it from here. If you take x equal to -1, f equal to -1, you substitute here. If x is equal to -1, this will be 2t minus b plus a into b minus a. Right. Now, if you cross multiply, it gives you a minus b equal to 2t minus b minus a. Now, if you take this, you can see that minus b cancel like this. Take this to the other side. You have 2t equal to 2a, so which implies that t is a. So if x is -1, t is a. Similarly, for x equal to 1, you find that t is b. You can do that. So you can see that this will map -1 to a and 1 to b. So this change of variable. So you'll be able to convert then this integral from -1, 1 to ab. So now for dx, you do the dx. So if you take d of this one in terms of dt, you get this, right? Because look at if I rewrite this, x, okay, this is x. You can see I say x is equal to this. Now if I take d of x, it will be 2 dx here. That is 2 by this. So dx from this, if I take differential here, differential of this will be 0, and differential of this will be 2 by b minus a dt. So that's what we get for the dx. All right, it will give us this. All right. Now, if you replace that in our expression dx, we take this, replace in our expression. in our change of variable, we will get this. So if you write the integral from a to b ft dt, right? This will give us, now you see that dt in terms of dx, if you replace dt here, you see that dt will be I divide, that is, I multiply here, you see, I multiply by b minus a and I divide by 2, so that will be b minus a by 2 dx. Now, if I substitute here, obviously we saw already that a and b will converted, will be changed into -1, 1. Now, f of t, I express t in terms of x, which will give us this. And now dt is all that. So for the dt, it will give us b minus a by 2, which is this one, right? So f of whatever is there, and then this one, b minus a, which I can bring in front, and therefore we get this expression. So that is it for the conversion. So you should be able to do that. Okay, now if you take this change, this one, this rule here, and apply it to this 3-point Gaussian rule, we'll obtain exactly this one. And if we do the same for the 2-point, we get exactly this. So please try to do this substitution. So this is another homework. Do the substitution. Use this formula. Substitution. So I will erase all these. So use this rule. Oh, sorry. So use this change of variable. Apply it to these two rules, this one and this one. And make sure that this is what you get for an arbitrary interval AB. Instead of -1, 1 for an interval AB, it should be in terms of A and B. So you should get this. Please do that and try also this example for, oh, that's Friday. Next time is Friday. Okay, so for Friday, please try to do this. Try to do this substitution and this example. Even though the solution is there already, but do that. So we will conclude this on Friday. And it will be the end of this second chapter. Of course, I promise that the result will be released today. So by the end of the day, check your email. No, not the email. It will be posted here on the e-learning. I mean, it will be on the e-learning platform, but also here on the Microsoft Teams. Okay, I hope you enjoyed today's class. God bless you and see you next time. Bye-bye.